Okay, hi everyone. I'm Cheng from RICE, and today I'm going to introduce our recent project PipeGCN, which is designed for efficient training of graph neural networks. So first, what is a graph neural network? A graph neural network is a special case of neural network, so it has multiple layers. And for one layer, a node first needs to aggregate the features from its neighbors. And in the first formula, here n represents the neighbor set of node V, and h represents the embedding vector of this node. So in the first equation, we have an aggregator. It combines the features of this node's neighbors. And then we have another function. It's called update function. It can combine the information that we collected. And one famous example of GNN is named GraphSAGE, where for GraphSAGE, we first simply calculate the average value of all embeddings of neighbors, and then we pass the result to a multi-layer perceptron. And the graph neural networks have many real-world applications. For example, we can use it for web graph analysis, or we can also use it to analyze a citation graph. And a graph neural network can also be used for social recommendation. But one challenge is that a real-world graph can be giant, and it may contain more than 1 million nodes, which cannot be stored in a single machine. So one straightforward idea is to separate a giant graph into several partitions, and we assign each partition to one worker. But remember that we are training a graph neural network, so each node needs to aggregate the features of all its neighbors. But sometimes, for example, in this figure, node 1 has a neighbor, node 3, but node 3 is assigned to worker 2. So during the training of a graph neural network, we sometimes need to collect the node features from a remote machine, and we call these nodes as boundary nodes. And for the nodes that belong to the partition, we call them inner nodes. Okay, now let's focus on the workflow of distributed graph neural network training. So at the beginning of each iteration, each partition only contains the features of all inner nodes. And because we want to perform some computation, we need to collect the features of boundary nodes. So this process requires some data transfer. And we here in this picture, I represent the features, the boundary features as the shadowed blocks. And then we can pass all features to one layer of GCN, and we can calculate the feature of the next layer. And we repeat this process. We collect the feature of boundary nodes again and pass these features to a layer of GCN. And because we are training a graph neural network, so we have a process of backward propagation. And during this process, we have an inverse process of communication. That means each node needs to scatter or gather the gradients, the feature gradients. And now we can conclude some challenges of distributed GCN training. The first challenge is that distributed GCN training requires frequent synchronization, because for each layer, we need to perform data transfer for its forward process and backward process. And this means that the number of synchronizations is proportional to the number of layers. And also, in our preliminary study, we find out that the communication overhead may take more than 80% total training time, which is not acceptable. So to this end, we propose PipeGCN to address the above two mentioned challenges. Okay, as we've analyzed in the previous slide, the main bottleneck of distributed GCN training is communication. And our idea is straightforward. Let's hide it. So let's focus on the red text in the second figure. So by comparing with the original GCN, we do not wait for the boundary feature of the current epoch. Instead, we use the feature from the previous epoch. And this allows us to perform communication and computation in parallel. And then now let's take the example of GraphSAGE again and consider how to apply PipeGCN on top of GraphSAGE. For GraphSAGE, as I introduced in the second slide, we need to calculate the average of the neighbor's features, and we also have a corresponding step for the backward propagation. And for our PipeGCN, if a node belongs to a boundary set here, in this formula, B represents the boundary neighbor set of this node. And if the node belongs to this set, we use its features in the previous iteration. Here, T in the superscript represents the number of iteration. And we can apply the same technique to the backward propagation. And now we have a critical question. Because we are not using a standard backward propagation and it's not a standard gradient descent, does PipeGCN converge? And our answer is yes. So in our project, we proved that PipeGCN converges and the convergence speed is proportional to epsilon power to the minus 3/2. And we also find out that the convergence speed is related to a constant E. And here, constant E in our analysis is bounded by the error incurred by the stillness. So this theorem further motivates us to design a technique to reduce the error incurred by the stillness. And this slide demonstrates the smoothing methods we proposed to reduce the error. Where in the original for implementing this smoothing technique, we replace the last term in the original PipeGCN with the smoothing method. Here, the original PipeGCN requires to use the still gradient or still feature, but here we use the exponential moving average of these terms. And here in this slide, we show some results. Here, the blue curves demonstrate the error of the original PipeGCN, and the other curves demonstrates the result of our proposed smoothing method with different parameters. And we can see that by using the proposed smoothing method, the error is always smaller than the original PipeGCN. And because we can apply this smoothing technique to either feature or feature gradient, we can propose 3 variants of PipeGCN. They are PipeGCNG, PipeGCNF, and PipeGCNGF. Okay, and in our experiments, we evaluate PipeGCN on 3 large-scale datasets. They are Reddit, Products, and Yelp. And we first compare the throughput of PipeGCN with existing full graph training platform. And we observe that PipeGCN and its variants is 4 to 25 times faster than the existing baselines. And also we study the accuracy and the throughput of PipeGCN. And we observe that PipeGCN and its variants maintain the full graph accuracy, and while it boosts the throughput by around 2 times. And we further analyze the convergence speed of PipeGCN and its variants. So in this figure, let's first compare the blue curve and the orange curve. Well, the blue curve is slightly covered by the purple curve, so maybe you need to take some time to find it. So in this figure, we find out that there is a clear gap between the blue curve and the orange curve. But when we use the smoothing technique, that is when we focus on a PipeGCNG or PipeGCNF, their convergence curve is significantly better than the orange curve. And if we apply the proposed smoothing technique to both gradient and feature, we can see that the purple curve performs similar or even better than the original GCN. And in our last experiment, we demonstrated the time breakdown of PipeGCN. Here in this figure, the yellow bar demonstrates the communication overhead. And we can see that with PipeGCN, the communication volume can be significantly reduced, and the reduced ratio is around 50% to 100%. So in summary, in this project, we we first figure out two efficiency bottlenecks of distributed graph neural network training. They are significant communication overhead and frequent synchronization. And also, to overcome these two challenges, we propose PipeGCN and analyze its convergence rate. And we further propose a low overhead smoothing method for reducing the error incurred by the students. And for our future work, because as I showed in the previous slide, we can see that by using PipeGCN, sometimes the communication overhead cannot be completely removed. So in our future work, we'd like to explore whether we can use quantization or sampling to reduce the communication volume. And also, we'd like to study whether we can combine PipeGCN with existing sampling-based methods to further boost the training efficiency. So that's all for my presentation. Do you have any questions?